All right, so in this lesson, we're going to talk about building functions from functions, or doing operations with functions. So let's start off with two given functions. We've got f of x, we've got g of x. F of x is the function 6 minus x. G of x is the square root of x plus 2. Okay, let's go ahead and find a domain for each of these functions. 6 minus x is linear. So we've got all real numbers for the domain of f of x. For g of x, we've got a radical, so we need to make sure that we have a positive radicand. So if we take x plus 2, make sure that it's positive or 0. Then x plus 2, make sure it's positive, subtract 2 from both sides. Then our x has to be at least negative 2. Okay, so now we can actually add, subtract, multiply, and divide whole functions themselves. So we're going to take a look at an example of one of each operation with functions. Okay, and we're going to use these two here. So let's start off with f plus g of x. We want to find it and its domain. And we can write that two ways. We can write it like it's given, or I think it makes more sense if you break it up into the individual function notation. So f plus g of x is the same thing as f of x plus g of x. We're just adding the two functions together. So let's take that expression, replace the given functions, and then we simplify if we can. In this case, we don't have any like terms. There's nothing we can simplify. So f plus g of x is 6 minus x plus square root of x plus 2. Okay, the domain, if we look at our finishing our end function, we have that radical again. So we've got to restrict our domain just like we did in g of x, to where it's from negative 2 to positive infinity, including negative 2. Okay, we also subtract functions. Same way we added. We start off with f minus g of x. We can rewrite it as f of x minus g of x, substitute in our functions, and we get 6 minus x minus the square root of x plus 2. A domain, same thing as before. It's still a function with the square root, and the x plus 2 is underneath the radical. All right, now let's multiply. If we have f times g of x, we can rewrite it f of x times g of x. Again, substitute the functions in for f of x and g of x. So we've got 6 minus x times the square root of x plus 2. We can use our distributive property to multiply the 6 and the negative x by the radical. So we get 6 times root x plus 2 minus x times root x plus 2. Domain, same thing in this composite function as well. All right, last one. Find f over g of x and its domain. So now we're dividing f and g. We can rewrite it like a fraction or with the division symbol. Substitute your function in for f of x on top, g of x on the bottom. We also want to find its domain, so we can't simplify this anymore. But when we find its domain, notice that now our radical is in the denominator. So we know the denominator can't be 0. So if we set that not equal to 0, we find that negative 2 is also not in our domain. So we take the domain we had and we take away that negative 2 from the domain.
Woo! Yay!
Composite functions, okay? You probably saw this in Algebra 2, so we'll go through this kind of quickly. We've got f of g of x. We've got this little open circle. It looks kind of like multiplication, but it's open in the center. We can read that as f composed with g, or f of g of x. I like to rewrite it like this. Kind of shows that we're taking that g of x and putting it into our function f. So that's really what we're doing. If we go back to our old function machines that we probably saw when we first saw functions for the first time, what we're doing in f of g of x is we're taking our, whatever we put in for x, our domain, we put it into our g function, whatever comes out is g of x, and then we take that, what comes out of our g function, and we put it into our f function. Whatever comes out of that is f of g of x. So let's look at an example. Again, we're given two functions, f of x and g of x. F of x is 1 minus x squared. G of x is the square root of x. If we go ahead and find the domain and range for each of these, this is a quadratic function, so its domain is all real numbers. The range, if we think about the graph of this function, it's really negative x squared plus 1. So we've got a parabola that's opening down and it's shifted up 1. You think back to your transformations. So we've got opening down, shifted up 1. So our range, since our parabola goes down forever, starts at negative infinity, but then it stops at 1, including 1. For g of x, we've got square root of x. So that's our square root function. So the domain is including 0 all the way up to all positive numbers. Same thing for the range. So we've got domain and range for each of our individual functions. Let's start off by finding f of g of x. All right, so f of g of x. So if I take my g of x function, root x, and I put it in where the x is in my f of x function, then I get 1 minus, and then instead of x, I'm going to use square root of x. Because f of x has that x squared, we get a squared on the outside. So 1 minus square root of x squared. Well, squared and square root are inverse operations, so we can simplify that to 1 minus x. But we've got to be careful with the domain and range of our composite functions. Since we're putting into our f function only what comes out of our g of x functions, then we've got to be careful about domain and range. So the domain for this function is only from 0 to infinity. So that's kind of inherited from the g of x function. The range comes from when we take those values and put them into our f of g of x function. So when we just put in positive values into this function, the only y values we get are all of our negative values up to positive 1. Okay, so from negative infinity to 1, including 1, we put in 0 there. Okay, one more example. We can also do g of f of x, so we can kind of switch the order of our functions. All right, so if we start off with our g function, which is the square root of x, and we take our f function and put it in place of the x, we substitute it in for the x, then we get the square root of 1 minus x squared. We can drop the parentheses, they're not necessary, so we have 1 minus x squared underneath the radical. Our domain in this case, since 1 minus x squared has to be a positive number, if we simplify that, then our only x values that we can put into this function are between and including negative 1 and 1. So that's our domain. So if we put only those values in, our only range is going to be from 0 to 1. So here's our 1 minus x squared function again. That range there only goes from 0 to 1, and taking the square root of those, same thing. All right, next up. Inverse functions. Okay, so inverse function, we know from when we first talked about functions that a function is only a function graphically if you can pass the vertical line test. So if you can take any vertical line in that function and it only touches one point, then it is a function. To test to see if a function has an inverse, or to see if it's a one-to-one function, then we can test it with the horizontal line. So if we can put any horizontal line anywhere on our function and it only hits 1 point, then it's a one-to-one function. Meaning that for any value that you plug into x, so any number in the domain has a unique y value associated with it. So you can only get a y value of 1 once on your entire function. You can only get a y value of 75 once. No other x value can have that. Okay, so if your function passes both vertical and horizontal, you've got a one-to-one function, and that function has an inverse to it. All right, we've got a couple examples here. Quadratic, we try the horizontal line test, touches in 2 places, so it does not have an inverse. But a good example of one that does is a cubic function. So anywhere we draw a horizontal line, it only hits in 1 place. So it is one-to-one. It is an inverse function. All right. There are 3 ways that we can find the inverse to a function. If we have the graph of an inverse function, for example, if we have our cubic function here, looks like it's shifted down 1, then if we graph the line y equals x, and we reflect our function over that line, whatever that reflection, whatever that image is our inverse for that function. Okay, numerically, if we take any coordinate on our function, so for example, this guy right here looks like 1, 0 on our f of x function. If we take our x and y coordinate and we switch them, so to switch places, so now we got yx, then that new point is the image of your original point on your inverse function. So 1, 0 becomes 0, 1 on your inverse. Okay, and then a third way, if you're given the equation of a function and asked to find its inverse. Okay, so example here, we've got x cubed minus 1. Let's first step replace the f of x function notation with a y. And then just like we did here, where we switch the x and the y coordinates, we're going to switch the x and the y in the equation and then solve for that new y variable. So then we start off y equals x cubed minus 1, switch the x and the y, we've got x equals y cubed minus 1, add 1 to both sides. Since we've got y cubed, we want to take the cube root. So cube root both sides, we've got y equals the cube root of x plus 1. And our notation for the inverse function is an f with a little -1 exponent. So we can read this as f inverse or inverse of f of x. Okay, so algebraically, switch the x and the y in the original, solve for the new y, replace the y with our inverse function notation. Please. All right, verifying inverses. Sometimes we want to verify to make sure that an inverse is, in fact, the inverse of a function. We can do that with a composition. So if we can take f of the inverse of a function and we get x out, and we can also do the inverse of the original function to get x out, then we verified that we do indeed have the inverse. Okay, so example, we're given our function, we find the domain and range, and then we go ahead and find the inverse. So if we've got the square root of x plus 2, switch the x and the y, solve for our new y, replace it with our inverse function notation. Then we get our inverse function is x squared minus 2. Our domain and our range flip as well. Since we're flipping the x and the y, domain and range flip as well. So the domain of our f function is the range of our inverse function. The range of our f function is the domain of our new inverse function. Now, the verify part. If we want to verify this function is an inverse of our original, we want to take the composition f of the inverse of f. So let's take our inverse function, put it into our original. So in this case, we get square root of x squared minus 2 plus 2. Simplify. Negative 2 and 2 is a 0 pair. Square root of x squared is x. So step 1, done. Next step is to do the, in a sense, the g of f of x instead of the f of g of x. So now we take f inverse of f of x. So we got the square root of x plus 2 squared minus 2. Square root and the square are inverses of each other, so they cancel out. We get x plus 2 minus 2. This is a 0 pair, so we're left with x. And we have verified that f inverse is indeed the inverse of f of x.